The errata for the 2005 National Electrical Code contains corrections to the text of the code that were discovered after the code was published. These corrections are necessary to ensure that the code is accurate and up to date. One of the most significant changes in the errata is the deletion of section 240.93. This section requires that all electrical equipment be grounded. However, this requirement was found to be impractical in some cases, such as when equipment is mounted on a non-conductive surface. The deletion of section 240.93 does not mean that electrical equipment can now be installed without being grounded. It simply means that the grounding requirements are now more flexible. Equipment can still be grounded using the methods specified in section 250 of the NEC, but it is no longer required to be grounded in all cases. It is important to note that the errata to the 2005 NEC is not a replacement for the code itself. The errata only contains corrections to the text of the code. All other requirements of the code remain in effect. To fully understand the implications of deleting section 240.93, it's crucial to delve into the specifics of grounding and bonding as outlined in Article 250. Article 250 provides comprehensive rules for grounding and bonding electrical systems, ensuring electrical safety and minimizing the risk of electric shock. The primary purpose of grounding is to provide a low-impedance path for fault current to return to the source, which in turn facilitates the operation of overcurrent protective devices like circuit breakers and fuses. When a fault occurs, such as a short circuit between a live conductor and a metal enclosure, the fault current flows through the grounding path. This high current triggers the overcurrent protective device to trip, disconnecting the circuit and preventing a potentially dangerous situation. Bonding, on the other hand, is the connection of all non-current carrying metal parts to create an electrically conductive path. This path ensures that all metal parts are at the same electrical potential, minimizing the risk of voltage differences that could lead to electric shock. Effective bonding also contributes to the overall effectiveness of the grounding system by providing additional paths for fault current to flow. Now, let's consider some of the specific grounding methods permitted under section 250. Firstly, the use of equipment grounding conductors is a common method. An equipment grounding conductor is a wire that connects the non-current carrying metal parts of electrical equipment to a grounding system. This conductor can be a separate wire, or it can be incorporated into a cable assembly. Secondly, metal raceways can also serve as equipment grounding conductors, provided they are properly installed and meet the requirements of the NEC. Metal conduits, such as rigid metal conduit and electrical metallic tubing, offer a robust and reliable grounding path. Thirdly, the use of the building steel as a grounding electrode is permitted under certain conditions. The building steel must be adequately grounded, and it must be connected to the electrical grounding system. This method can be particularly effective in large buildings with extensive steel structures. Moreover, understanding the difference between grounded and ungrounded systems is essential. In a grounded system, one of the circuit conductors, typically the neutral conductor, is intentionally connected to ground. This provides a reference point for voltage and helps to stabilize the system. In an ungrounded system, none of the circuit conductors are intentionally connected to ground. Ungrounded systems offer some advantages, such as increased resilience to single ground faults, but they also require careful monitoring to detect and address ground faults promptly. The removal of the requirement in section 240.93 to ground all electrical equipment provides more flexibility in certain situations. For instance, when equipment is mounted on a non-conductive surface such as a fiberglass enclosure, grounding may not be necessary or practical. However, it is crucial to conduct a thorough risk assessment to determine whether grounding is required in such cases. Factors to consider include the type of equipment, the operating environment, and the potential for exposure to electrical hazards. Even with the deletion of section 240.93, there are still many situations where grounding is required. For example, metal enclosures that house electrical components must typically be grounded to prevent the risk of electric shock. Similarly, equipment located in hazardous locations, such as areas with flammable gases or dust, often requires grounding to minimize the risk of ignition. The NEC provides specific requirements for grounding in different types of occupancies, such as residential, commercial, and industrial buildings. These requirements take into account the unique electrical hazards present in each type of occupancy. For example, in residential occupancies, the NEC requires the grounding of electrical outlets and lighting fixtures to protect occupants from electric shock. In commercial buildings, the NEC may require additional grounding measures to address the higher electrical loads and more complex electrical systems. In industrial facilities, the NEC provides detailed requirements for grounding in hazardous locations and other specialized environments. When making changes to electrical systems, it is essential to consult the latest edition of the NEC and any applicable local codes. The electrical codes are constantly evolving to address new technologies and emerging safety concerns. Failure to comply with the latest codes can result in fines, project delays, and, most importantly, increased risk of electrical hazards. Moreover, it is crucial to use properly listed and labeled electrical equipment. Listing and labeling indicate that the equipment has been tested and certified by a recognized testing laboratory such as Underwriters Laboratories or Intertek. This certification provides assurance that the equipment meets established safety standards and is suitable for its intended purpose. When selecting electrical equipment, always look for the listing and labeling marks to ensure that you are using safe and reliable products. In addition to grounding and bonding, overcurrent protection is another essential aspect of electrical safety. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow. These devices automatically interrupt the circuit when the current exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. Circuit breakers are reusable devices that can be reset after they trip. Fuses, on the other hand, are one-time devices that must be replaced after they blow. The selection of the appropriate overcurrent protective device depends on the ampacity of the circuit conductors and the characteristics of the equipment being protected. The NEC provides detailed requirements for overcurrent protection in Article 240. Article 240 covers the requirements for overcurrent protection devices intended to protect conductors and equipment. It addresses topics such as the selection and installation of overcurrent protection devices, including fuses and circuit breakers, to ensure that they provide adequate protection against overloads and short circuits. Proper coordination of overcurrent protective devices is crucial to ensure that the device closest to the fault trips first, minimizing the impact on the rest of the electrical system. Selective coordination involves carefully selecting and setting the overcurrent protective devices so that they operate in a coordinated manner. This requires considering the time current characteristics of the devices and the potential fault currents at different points in the system. Furthermore, surge protection is becoming increasingly important to protect sensitive electronic equipment from voltage transients. Voltage surges can be caused by lightning strikes, utility switching, or even the operation of other equipment in the building. Surge protective devices divert the surge current away from the protected equipment, preventing damage. Surge protective devices are available in various types and configurations, including whole-house surge protectors, which protect the entire electrical system, and point-of-use surge protectors, which protect individual pieces of equipment. When installing surge protective devices, it is important to follow the manufacturer's instructions and the requirements of the NEC. Proper grounding is essential for the effective operation of surge protective devices. In addition to the technical aspects of electrical safety, it is also important to consider the human factors. Electrical work can be dangerous, and it is crucial to take precautions to protect yourself and others from electrical hazards. Always to energize circuits before working on them, and use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not qualified to perform electrical work, hire a licensed electrician. Electrical work should only be performed by qualified individuals who have the necessary training and experience. Qualified individuals are familiar with the NEC and other applicable codes and standards, and they have the skills and knowledge to perform electrical work safely. When hiring an electrician, check their credentials and references to ensure that they are qualified to perform the work. Moreover, regular maintenance and inspection of electrical systems are essential to prevent electrical hazards. Over time, electrical components can deteriorate and wiring can become damaged. Regular inspections can identify potential problems before they lead to accidents. Maintenance tasks, such as tightening connections and replacing worn components, can help to keep electrical systems operating safely and efficiently. The frequency of maintenance and inspection should be based on the type of equipment, the operating environment, and the manufacturer's recommendations. In conclusion, electrical safety is a multifaceted topic that requires a thorough understanding of the NEC, proper installation practices, and ongoing maintenance. The deletion of Section 240.93 from the 2005 NEC does not diminish the importance of grounding, but it does provide more flexibility in certain situations. By following the guidelines outlined in the NEC and taking appropriate precautions, you can minimize the risk of electrical hazards and ensure the safety of yourself and others. Always remember to consult with a qualified electrician if you have any questions or concerns about electrical safety. Electrical codes and standards are updated regularly, so it's essential to stay informed about the latest changes. Attending training courses and seminars can help you to keep your knowledge and skills up to date. The National Fire Protection Association, or NFPA, offers a variety of resources on electrical safety, including training courses, publications, and online tools. These resources can help you to stay informed about the latest codes and standards and to improve your understanding of electrical safety principles. Furthermore, promoting a culture of safety in the workplace is essential to prevent electrical accidents. Encourage employees to report any electrical hazards they observe and provide them with the training and equipment they need to work safely. By creating a safe work environment, you can reduce the risk of accidents and injuries. Consider implementing a lockout/tagout program to ensure that circuits are de-energized before work is performed. A lockout/tagout program involves placing a lock and tag on the disconnecting means to prevent the circuit from being accidentally energized while work is in progress. This program helps to protect workers from electrical shock and other hazards. In addition, use ground fault circuit interrupters, or GFCIs, in areas where there is a risk of electric shock. GFCIs are designed to protect people from electric shock by detecting ground faults and interrupting the circuit. GFCIs are commonly used in bathrooms, kitchens, and other wet locations. Make sure that all electrical equipment is properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect people from electric shock and prevent damage to equipment. Regularly inspect electrical cords and plugs for damage. Damaged cords and plugs can be a fire hazard and can also cause electric shock. Replace any damaged cords and plugs immediately. Avoid overloading electrical circuits. Overloading a circuit can cause the wires to overheat, which can lead to a fire. Use extension cords sparingly and never run them under rugs or furniture. Keep electrical equipment away from water. Water can conduct electricity, so it is important to keep electrical equipment away from water. Do not use electrical appliances in the bathroom while you are wet. Be aware of the location of overhead power lines. Overhead power lines can be extremely dangerous. Never touch a power line with any object and stay away from downed power lines. If you see a downed power line, call the utility company immediately. Finally, remember that electrical safety is everyone's responsibility. By following these tips, you can help to protect yourself and others from electrical hazards.